Okay, so I'm working through section R.3, going through the review material with you. And I'm on up to page 28. If you're following along in your book, this is page 28. I'm on example 7, C part. So on C part, we have three things multiplied together, actually. We've got an r squared times 3r plus 2, quantity 3r minus 2. What I would recommend, and you can multiply in any order you want, for example, if you had 2 times 3 times 4, when you've got three things you're multiplying together, you can multiply those however you like. You could go 3 times 4 is 12, then 12 times 2 is 24. Or you could go 2 times 3 is 6, 6 times 4 is 24, or 2 times 4 is 8, then 8 times 3 is 24. It's all 24. You can multiply in any order. So that's true with our polynomials. There's three things to multiply. You multiply the way that's easiest, you think. So what I think would be easiest is to use the special pattern that we just learned, which is when you have the sum and difference of two terms, you can just say it's going to be just the first term squared minus the last term squared. We learned in the last lecture that x minus y times an x plus y will always be x squared minus y squared. The middle terms will drop out. So when we look at this example, can you all see all that? I'm going to scoot it over just a little bit. I'm not sure it's, yeah, it's in your screen. Just checking. So when I look at this, I can multiply that by the special pattern and tell that it's just going to be 3r, both parts of that squared, which is 9r squared, and then the 2 squared, which is 4, and a minus between them. So this times this is this. Then I still need to times it by the third part, the r squared. So that's how I would do it. Then distribute the r squared into my parentheses. It would make 9r to the fourth because we add exponents when we multiply, and minus 4r squared for that. Okay, next thing, on page 29, we see a green box where all the important rules in our book lie. So we see the green box has our special products. And if we can get this straight in our mind, it will help us whenever we do the next section. We're going to do the reverse of the special products. We're going to factor the special products. So anytime we see this, we'll be able to work backwards into its before. So the special products we see here are the one we just did, x plus y times x minus y. When you FOIL that, you'll always miss the middle parts. They're the opposites of each other. So that's called the difference of squares. Sum and difference of terms multiplies to be the difference of squares. So when we do this in the next section, we want to be able to work backwards to that in factoring. Then the other one is when you square a binomial. Now listen guys, this is one of the trickiest ones in my experience in teaching algebra that we have mistakes on, because it's real easy just to say x squared plus y squared. Real common mistake. But there's always middle parts to this. When you FOIL this, x plus y to the second would mean x plus y times x plus y. Anything squared means that times itself. Well, when we FOIL that, let's go through. First is x squared. The outer is xy. The inner is another xy. And the last times last is y squared. So you get a double portion of the middle terms. Instead of dropping out, when we square a binomial, instead of the middles dropping out, because they're the same term, they double. So we double the middle terms, and we get x squared, 2xy's, and y squared. So the pattern is, anytime you've got the square of a binomial, it is, unlike the one above it, it is the square of the first and the last, plus double the two in the middle times together. So that's the square of a binomial, and the word for this is perfect square trinomial. This is called a perfect square trinomial. So when we're factoring in the next section, when the front and the back numbers are perfect squares, and the middle is their square roots times together and doubled, and this happens, we'll be able then to jump over to the factoring of it. It also works when we have a negative number, x minus y squared. The only thing that's different about that, if we go through the FOIL method, is the middle term is negative. It'll be minus 2xy plus y squared. All right, so we have some examples. Follow along in the book. We're on example 8. Example 8, We've got some of these special products to practice, and I won't do every one of these, so I encourage you to anything that I don't get to in the lecture that you look at as well in your own time. Okay, the first example would be the sum and difference of two terms. So what we've learned from our special products is we can just multiply the first or square the first and get 9p squared. And then when we do the outer, the inner, they drop out. So then we just do the last times last, and it'll be minus, or just the last term squared. 11 squared is 121. And so again, I want you to be thinking in the next section, we see something like this, a binomial, and we're asked to then factor it. So anytime we see the difference of squares, we can then go the reverse direction when needed. Sometimes we need a factor to reduce something, and sometimes we need to multiply to reduce something. It depends on the process, whatever we're asked to do. So we do both of those along the class. Let's look at D part. 2m plus 5 squared. So that's going to be the binomial squared, the special product we talked about. Now, if this gives you any grief, just write it down twice and FOIL it until you get comfortable with the pattern. It will help you if you get these little tricks down pat, but it's not required. You can always FOIL this together, and you will see the first is 4m squared. The outer is 10m, and so is the inner. They're exact same signs, so they just double. And then the last times last is 25. Now, like I said, preferably, you'll know the pattern is when you see a binomial squared. Square the first, that's the 4m squared. You times these two parts together, 10m, and then double it is 20m, and then the square of the last, 25. So that's the pattern that we try to use. All right, moving on over to example 9. So they take all of this and kind of go extreme on example 9, and some things go further than we regularly will do. The FOIL method is like an everyday thing. We'll use that all the time. But I would say example 9 is kind of the extreme version, just to press your skills to make sure you're getting this at high level. But it is a little further than we typically would have in everyday problems. But it does fall into this pattern that we just talked about. Let's see if we can see it. Okay, so we've got 3 terms times 3 terms, which sometimes means just distribute a lot, and we could do that. But actually there's a pattern here. We've got, if you thought about this as being an x plus y, and this is the same, x minus y. It's our pattern. That's an x plus y times an x minus y. So without going through the entire FOIL method, we should know that the pattern says it'll be x squared minus y squared. So it should just be this thing squared, 3p minus 2 squared, minus y squared, 5q squared. And then we need to clean that up further, but that does shortcut it quite a bit. So still we're using our special pattern we learned here. This is a binomial squared. So what we learned is you square the first, 9p squared, times these together and double for the middle term, and then square the last. So using our special pattern, and then minus each of these squared. I'm going to go ahead and call 5 squared 25, and then q squared. And I think that's how they leave the answer, nothing else combines, and that is as simplified as we can get it. Like I said, there's other ways to get there, but that would be using our new patterns. All right, let's do example B. And y'all know that you can just pause this anytime you need and re-look at that again if needed, or shoot me an email if you need me to explain something further or do another example. All right, x plus y to the third, that is not necessarily a pattern that we have just talked about. It's not in the 2 that we saw, but we can kind of use that. It means x plus y times x plus y times x plus y, right? To the third power means that times itself 3 times. So what we've got here is the binomial squared, x plus y to the second, you could think of that as. So if you're wanting to use the shortcut pattern, it's there for us a little bit anyway. It doesn't take care of the whole thing, but it will help us do this part. Remember, a binomial squared is square the first, times together and double that, and then the square of the last. Then we still have to times it by x plus y. So there's no special pattern for that. That just needs to be all multiplied out. So each of these times each of these, so just distribute it, x squared times x squared times y. 2xy times x, 2xy times y. Then distributing the y squared times x, and y squared times y. Once you get all your terms, combine any like terms. X squared y and 2x squared y makes 3x squared y. 2xy squared, and this would be, you could turn that around, that's xy squared, just turned around order, but it's equivalent. So there's 2 and 1 makes 3 of those. And then lastly, the y cubed. There's actually a little pattern to that in Pascal's triangle. If you've done that in a previous class or something, there is a way to kind of get there a bit, but we don't get into it in this class. And this section doesn't mention it. But there is actually a little shortcut if you've maybe had that question. All right, so multiplying. And the last thing we're going to do is the division example. So we've added, subtracted, we've used the exponent rules, we've done all this multiply. The last thing in this section is dividing polynomials. So we don't do this a whole lot either. Some things I'm telling you we do all the time with the FOIL method and factoring, but dividing doesn't come up a super amount, but it does in one little section that we do. So it's good to be thorough. This is one of the algebra rules, to be thorough, the foundations of your algebra. So if we have a polynomial, okay, here's our polynomial, and we are dividing it by a polynomial, like so. One method for doing this will be factoring. We're going to see that in the next section in R.4, how we can sometimes factor, but nothing here is factorable actually, it's just a pure division problem. So we can set this up as long division, old style arithmetic long division. And we'll say this is divided into that. Now, when you set these up as division problems, you want to make sure they've put this in descending order with no places skipped. Say they skipped the m squared and went straight to 5m, you'd need to put a 0 placeholder there. So it needs to be in order, m to the third, m to the second, m to the first, and then the constant. The same thing with your divisor, it needs to be in order with nothing skipped. So that's the startup, and then 0 placeholders is needed. In your example 11, you can see that they did need a placeholder in that. All right, so then we divide this first term into this first term. We say how many times does that go into that, just like with old style division. It goes 2m squared times, because if you were to multiply these together, you get exactly that. Then we also multiply it through this polynomial, so distribute it through your polynomial, and that'll be negative 2m squared. So this times this, negative 2m squared. Like in old style division, long division, we subtract those two lines. So when I subtract, the subtract will distribute through that polynomial and change both of the signs. Then we use our add rules down. So that should always cancel if we've done this correctly. This, you should have like terms with a line up if you got that correct as well. Negative 8 and 2 is negative 6m squared. And then we bring down the next term, just like old style long division, and then we repeat that process. So 2m into negative 6m cubed, or squared, because this times this, it needs to equal exactly that. So whenever I change the sign, it cancels out. And then distributing it here, subtract changes the signs of those terms, and then you should have like terms that should cancel. And then bringing down the last term, divide one more time. And notice that I will have a remainder when I change the signs. Remainder is 7. You can put the remainder over the divisor, and then that's the answer to your division.